The question is, using the property of determinant, prove that in the first part the determinant a minus b minus c 2a and so on is equal to a plus b plus c whole cube, and in second part x plus y plus 2z xy and so on is equal to twice x plus y plus z whole cube. Now to solve this question, first of all, taking the left hand side of the determinant given in the first part, that is a minus b minus c 2a 2b b minus c minus a 2b 2c c minus a minus b. So on observing the determinant, I see that if I add all the elements in the column 1, I get the total as a plus b plus c, and similarly for the second column and similarly for the third column. Okay, now to prove this result a plus b plus c, the first thing what I'm going to do, I'm going to apply the property that r1 is changed to r1 plus r2 plus r3. That is, to the element of row 1 I'm going to add the elements of the second row and the third row. So I'm going to obtain the determinant like this: a minus b minus c plus 2b plus 2c, 2a plus b minus c minus a plus 2c, and 2a plus 2b plus c minus a minus b, and the remaining rows, the second and the third rows, as it is. On adding them or on solving the elements in the first row, I am going to get this as equal to a plus b plus c. All the three terms in the first row as a plus b plus c. Now I am going to take a plus b plus c as common from the first row. So I am going to get the determinant as a plus b plus c into 1 1 1, and the second row and third row as it is. Now because the elements of the first row are 1 1 1, now I am going to apply the step so that these two elements become 0. Applying the property that c2 is changed to c2 minus c1 and c3 is changed to c3 minus c1, I am going to get a plus b plus c times the determinant, the first row, first column as it is, 1 minus 1, b plus c minus a minus 2b, and 2c minus 2c, and 1 minus 1, 2b minus 2b, c plus a minus b minus 2c. Right? On simplification, I am going to get this as ABC as it is, first column as it is, first term 0, b plus c minus a minus 2b would give me minus b minus c minus a, 2c minus 2c is 0, 1 minus 1 0, 2b minus 2b 0, and this will be c plus a minus b minus 2c will be minus c minus a minus b. Now I am going to expand this determinant along the first row because two elements of the first row are 0. So expanding along the first row, I am going to get this as ABC into 1 into the determinant obtained by removing first row and first column, that is minus, this term can be written as minus a plus b plus c, this term can be written as minus a plus b plus c. So the determinant obtained by removing first row and first column would be this determinant, and because the next two terms are 0, so plus 0 for next two terms. Okay, now on simplifying this determinant, this will be equal to a plus b plus c into a plus b plus c whole square, or a plus b plus c whole cube. So we have to prove that the determinant was equal to a plus b plus c whole cube. So this is how we are going to prove the first part. Now we are going to solve the second part. Taking the left hand side of the determinant given in the second part, we have x plus y plus 2z xy, z y plus z plus 2xy, zx z plus x plus 2y, and we have to prove that this determinant is equal to twice x plus y plus z whole cube. So first thing what we can observe here is this, that if we add the elements of column 2 and column 3 to the element of the first column, I'm going to get this as twice x plus y plus z. So using this analysis of this determinant, I'm going to apply the property that C1 is changed to C1 plus C2 plus C3. So on adding the elements of column 2 and 3 to the elements of column 1, I'm going to get x plus y plus 2z plus x plus y, z, y plus z plus 2x plus y, z, x, z plus x plus 2y. Okay, and column 2 and 3 as it is. On adding, I'm going to get this as 2 times x plus y plus z for all the 3 terms in the column 1. This twice x plus y plus z can be taken common. So taking 2 times x plus y plus z common from C1, I'm going to get this as twice x plus y plus z into the determinant 1, 1, 1, x, y plus z, 2x, x, y, y, z plus x, 2y. Now because the elements of the column 1 in this determinant are all 1, so we can easily make them equal to 0, so that we can obtain 2 zeros in the first column. So taking the determinant and applying the property that R2 is changed to R2 minus R1 and R3 is changed to R3 minus R1, I'm going to get this determinant as twice x plus y as it is, 1 minus 1, y plus z plus 2x minus x, y minus y, x minus x, z plus x plus 2y minus y. So this would give me 1, 0, 0. This x subtracts from this term to give me y plus z plus x, this 0, y minus y 0, z plus x plus 2y minus y is y. Now we are going to expand this determinant along the column 1, and we are going to get this as twice x plus y plus z into 1 into the determinant obtained by removing first row and first column, that is x plus y plus z, 0, 0, x plus y plus z. The terms are rearranged as x plus y plus z, you can see here, because the next 2 terms of the column 1 are 0, so plus 0 plus 0. On simplifying this determinant, I am going to get this as twice x plus y plus z into x plus y plus z whole square, which is equal to twice x plus y plus z whole cube, and which proves the question which is given in the second part.